Hello again, Sarah Miller here, and this week we'll be talking about specific heat capacity with a special focus on water. Specific heat is a measure of heat capacity, and heat capacity is how much heat a material can store before changing temperature. A good example of materials with different heat capacities is a pot on the stove full of water. Think about how much longer it takes the water to get hot than the pot. This is because the water has a higher heat capacity and can store more heat before changing temperatures. Specific heat is typically measured in joules and kilojoules per 1 gram of mass, with Celsius or Kelvin as a measure of temperature. A substance's specific heat can be affected by temperature and pressure, so specific heat is typically determined at constant temperature and pressure, typically 25 degrees Celsius. The equation for specific heat is Q equals C or mass times C times delta T. Q is equal to the amount of heat, C is the specific heat capacity, M is the mass, and delta T is the change in temperature. So what specifically is the heat capacity of water? Water has a rather high specific heat capacity of 4182 joules per kilogram degrees Celsius because it requires more energy than other substances to raise the temperature. Just to give you a benchmark, the specific heat capacity of steel is 466 joules per kilogram degrees Celsius. Air is 1012 joules per kilogram degrees Celsius. Olive oil is 1790 joules per kilogram degrees Celsius, and elemental hydrogen is 14,304 joules per kilogram degrees Celsius. Water's high heat capacity is due to the weak bonds that occur between hydrogen and oxygen atoms of adjacent water molecules called hydrogen bonds. When heat is absorbed, the hydrogen bonds are broken and water molecules move around each other freely. When the temperature of water decreases, the hydrogen bonds are formed and they release quite a bit of energy in the form of heat. So now that we know why water is especially hard to heat up, where the heat goes, and some terms that will help us determine how difficult substances will be to heat up, let's go to the demonstrations. So initially I mimicked the video and found that indeed filling a balloon half with water caused it to become pop proof. And as long as you kept the flame in the area where the water was resting, it didn't pop, which was kind of boring. And then I got creative and thought maybe I'd put isopropyl alcohol in a balloon, but
we have 22 grams
did not. That was just a video from YouTube. That was a joke.
Here.
That was not me.
Wait,
And so here we have a balloon
have
with
22
flour,
grams of
and
water.
this is a bowl
Weighed
full of the same mass of water. And here's the three balloons lined up. One has 22 grams of flour, one has 22 grams of water, and the middle one is full of air. And the three have candles lined up to be placed under them. And let's see what happens. So the middle one popped, and we're going to do this again. Oh, and the flower one popped. Wow, okay. So that's expected. So we found on the internet beforehand that flour has a specific heat capacity of about 1.8. So it makes sense that this let's see, the order of the popping would correspond to the heat capacity of the balloon contents, with the balloon with the lowest specific heat capacity popping first, which was air only, and the highest specific heat capacity taking the longest to pop, which was water, which will pop soon. Actually, there's a small hole. um, yeah, and so it just diffuses slowly. Um, and so yeah, what we learned is that yeah, the balloons were popping in order of heat capacity, and so yeah, we validated the information we found on the internet, which is that um, the water took the longest, the empty balloon went first, and the flower balloon was in the middle. And this all makes sense if you look at the specific heat capacity for each of the substances. And thank you for listening.